Hello, this is the next video in my series on maximum likelihood estimation. And this video we're going to look at the derivative of the trace. And the trace is a square matrix function where it adds the diagonal elements. The first two videos, and I suggest you go back and watch them, and that's the derivative of a determinant with respect to a matrix and the derivative of a quadratic form with respect to a vector. And a lot of the notation and nomenclature we're going to use in this video. So let's jump right in. So background first, let's let A, B, and X be n by n matrices. Let the inverse of X exist, and we're going to let little a and b be vectors, n by 1 vectors. Now notationally, I kind of messed up a little bit, but I think you'll get what I'm saying. So if we let X be represented by some matrix, call it Xij, and then in reality I could have skipped this last piece here and just gone with this. But it's whatever the ij element is, then you put ij around it in parentheses, and that becomes the ijth element of X. And that'll make more sense on the next one. But the trace of X is add up these diagonal elements, which the indexes have to be equal. So it's going from k equal 1 to n of xkk. So now this one, let's let the matrix multiplication A times X, the ith element is this. So this represents the ith element. So you put parentheses around it, meaning it's the ith element, and you put parentheses around that, and it means that represents this matrix. Okay. And the trace of this is if this is a typical element. So the trace is down the diagonal when I and j equal. And so we have to go from, say, introduce another index called L and let L go from 1 to n, but this I and j are equal, so they're both L. And that's what this represents. So we have this same setup here, but we let I and j equal, and that's L, and it goes from 1 to n. So this is the trace of this. And we're going to use these in this video. And this is review, and if this is something you haven't seen before, then I would suggest looking up the trace and how it can be represented. So this one is XBX. The three matrices can be represented like this. So X, B, and X, where these are X, of course, is an element from here, and B is an element from here, and this sum, double sum, represents the ijth element of this matrix. And again, the trace of this, we're going down the diagonal, so I and j are equal, so we have to introduce a new variable called index called m, until the trace of xbx is m, it's over m, l, and k, and this is the typical representation of it. So let's start taking derivatives. So here, the derivative of the trace of x. Now, the trace is a scalar, so because we're adding the elements and you get a number back. So this is the derivative of the scalar with respect to a matrix. And so we represent the trace by this. It's the sum of those diagonal elements. And then you need to go back and look at the derivative of a determinant, with respect to a matrix, to look at this notation and why it's like this. But since it's a scalar, it's on the numerator in here, and with the denominator with the partial with respect to, basically this X matrix, it transposes. So the N1 element here actually is the 1N element here. And the ij element of this is actually the ji element of this one. So you take the partial of this with respect to x1, partial of this with respect to n1, partial with respect to 1n, n, and there's only one time that this equals, 1, 1, and then the partial of it is 1. And these over here, since k and k have to equal, they can never be in 1. So this is always 0. And actually every off diagonal element 0. And this would be 1. So the derivative of the trace of x is the identity matrix. So now let's look at the trace of ax. And then that can be represented as this double sum. And then we want to take the partial with respect to x. Oh, and a side note, I'm doing this, the 3 videos, my 3 last videos, the derivatives are all with the goal of finding the maximum likelihood estimators of a multivariate normal distribution, the mean vector and the variance covariance matrix. So here, this, again, this is a scalar. We'll take the derivative with respect to a matrix, so it's going to be a matrix. And so that since this is a scalar, it's in the numerator each time, and then the derivative with the partials. Remember, it's a transpose. So this the n1 element is it's the 1n element in this matrix, and this is the 1n, so it's the last one on first row, but it's the nth row in the first column here. It's transposed. And so now when we look at the partial of this, when can this sum be a 1, 1? Well, that's when the a is a 1, 1. So the partial of this with respect to x1, 1 is just a 1, 1. Now this one, you have to think about it. So this is the n1 element of the matrix. So when can this double sum, it's all 0 unless this one is n1. But if this is n1, that means this is 1n. So the partial of this with respect to n1 is a1n. And so, and you do that for each of these, and you get this back, which is just the A matrix. It's the original A. So the partial derivative of the trace of A times x with respect to the matrix x is just A. Okay. Now, by default, we get some easy ones. So the partial of the trace of AXB, now since you can flip these around, and you can't do it willy-nilly, there's a method to it, and one of those you can take the last one and move it to the front, and then the trace of this and the trace of that's the same. So then when we take the partial, this looks just like before. You let this AB be the matrix C, for instance, and it looks like this. And so we get this matrix in the front back. And if the partial of the trace of AXB, where these are vectors, actually this is a scalar, so this is a 1 by 1. So we don't even need the trace. But what the trace helps us, it allows us to rearrange this. So we can move the B to the front and we get this. And then this is a matrix. So we just proved up here that the derivative of this trace is just whatever the matrix is out front. So it's B times A. So for this result, so let's let A be a function of X. So this is, it doesn't have anything to do with a matrix, the X. It's just a random variable X. And then let's let B actually be a function of X also. So we want to take the partial of A times B, or the ith element of A times B. Okay, so and this matrix multiplication can be represented like this. The ith element of this is this sum from 1 to n, aik, bkj. And then we're taking the partial with respect to it's a scalar. So it's a scalar and biscalar. Now here, since they're both functions of x, and they're numbers, we just take we have to use the product rule. So in the derivative, partial goes through this sum, and then we get this. So the sum stays the same, and then you get AIK, the derivative or partial of B with respect to X, plus the partial of A times B. And this, since it's a sum, of a sum, you can break it up into two pieces and get this. But then, remember, this is the ijth partial, it's the ijth element of this matrix. Well, this is representative of matrix A times a matrix B, the partial of B with respect to X. So this ends up being a matrix if you look at the first page and kind of back solve it. So this says that the derivative of AB, so we just did it for the ith element, and then the form of this allows us to go back to matrix multiplication. So the derivative of AB is equal to A times the partial of B with respect to X plus the partial of X, partial of A with respect to X, and then B times B. And the reason we do this is because of the next step. And this is kind of neat if you want to take the partial of an inverse matrix. So here we know this identity holds. We're going to let A be a function of X, but we're just going to call it A. So we know this exists. And now if we take the partial of both sides with respect to X, the scalar X, then we just learned that this product is this. It's A inverse times the partial of A with respect to X plus, partial of A inverse with respect to X times A. And since the identity matrix, there's no X's, it's constant with respect to X, the partial is 0 everywhere. And then we can subtract this to the other side, and that's what this is. And then since A has an inverse, we can take the inverse of both sides, and we get this, and then we're finished. And then we're going to use this. This is kind of a neat result. The partial of an inverse matrix with respect to X is this function here. So let's look at the trace of the X inverse. Now we're going to do it. Now eventually we want to take the partial of the trace of this X inverse with respect to the matrix X. But let's just do it for one element first and use the previous result. So since the trace has a neat property that you can take the partial through, so it's the trace of the partial of X inverse with respect to the ijth element. And then so using the previous result, we get this right here. Now this here ends up, the partial of X with respect to Xij, this ends up being a matrix of all zeros except for one element is 1. The ijth element is 1. Okay, but let's let B be this matrix here. And then we have X, B, X. And so if we use the notation on the first page, we get this triple sum of this trace. So this trace is this. But remember that unless L and K, so this represents the LKth element of this. But remember, the partial of this is all zeros except for a 1 in the ij element. And so this is always 0 unless L is I and K is J. So all these double sums are sort of, they make this be 0 unless this is I and that's J. So we can just get rid of that. And so this, because of this partial here, is actually the sum, the minus of this sum. Well, this is, if this is the ijth, the partial of with respect to ij is this, then that implies that the partial of this, the matrix, the trace of the inverse of x with respect to the x is this. And the tricky part here is, remember, this is the ijth element, okay? But when you take the partial, the ijth element here ends up being the jith element here. So it's actually backwards. So the ij element of this ends up being the jith element here. So it's kind of, you have to, let's look at that. So here, so the trace, so this is the ijth element, I and j. So think of it as the, I is first and j is second. But here, so if since this is multiplication, we can flip them. So this acts like I and this is j. So it actually looks like the transpose. But when we take the partial, remember that the ijth element, if we take the partial of the ijth element of this, it actually ends up being the jith element of this, and that's why this ends up being this. And so I would recommend, writing out the matrices and doing as much detail as you need to make sure that you understand that. So now let's look at this. So let's look at the partial of b times x inverse with respect to the ijth element. Okay, so this is a matrix, product of matrices times a scalar. So we learned from before that it's b, and then the partial of this x inverse with respect to xi, plus the partial of b with respect to xi times x inverse. Now, since this is we're going to let b be a constant matrix, so it's not a function of x. So this goes to 0, and we're left with this. Well, the partial of x inverse we learned was this. So it's minus b x inverse, and the derivative, the partial of this is x inverse, the partial of x with respect to xij, and the x inverse. So now this is where I couldn't really figure out a good scalar notation for this product or the ijth element, so I just multiplied it out. So ignore this bottom piece here. So to write this piece out, so the minus b stays the same. And remember, this is a matrix of all zeros but 1, 1. And so this product ends up being this, where the x1i inverse, that's the 1ith element of this, and it ends up being this matrix. So then when you take this product times this, you get this. And so it's the first row times the first column, and that's what this represents. So this one would be the first row times the nth column. And you do that for all those and you get this. And the reason we're doing that, because eventually we want to take the trace of this function. So now we want to take the partial with respect to ij of the trace of this matrix. So, the partial of this with respect to ij we just did on this page. All right, so we did this, which ends up being this matrix. So then if you take this matrix and find the trace, so this piece is this matrix, and so you take the partial in and then you get that big matrix, and then we want to take the trace of it. So the trace of this is just going down the diagonal, which is this. Okay, And this is matrix, or these are all scalars, so you can change around. I like to put the B in the front, and then this goes in front because that represents the IJ element. You know, the partial with respect to IJ element is this. And this kind of looks like a matrix multiplication, X times B times X. But sort of the I and the J elements are reversed of what we did on that first page. But that actually works out well. So when we take the partial of the trace of B times X inverse with respect to X, then since this looks like the transpose, and when you take the ijth element here, it actually is the partial with respect to the jith element, so it gets transposed back. And so this ends up being this product here, which is going to be very helpful in the multinomial. So let's do two quick examples. So let's take the partial with respect to this. Now, with respect to the matrix X. So this is actually a 1 by 1 matrix. So we can take the trace of it and it doesn't change it because it's 1 by 1. But taking the trace allows us to manipulate this. So if we move this to the front, we get this. And then this is a matrix times this matrix. So we just did that right here. So this is going to be minus X inverse times this matrix X inverse. And then the second quick example is we take the partial of this respect to X inverse. So these are the same here. So this is a 1 by 1, so we can take the trace and it doesn't change it, but it allows us to move that out front. And then the trace of this with respect to the, say just X is just what's in front. So we get this. Well, I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. The next video is going to find the MLE estimates of the multivariate normal distribution. Thanks. Bye.